Here we are, another day. Here is a new topic for you called exponential functions, but actually it's not a new topic. It's just sort of an update of something you already know how to do. There is a fan in the background because it's like April, but still in the upper 70s. So hopefully it's not making too much noise over the recording. So just a question. You might have heard this little poser before, but take a pick of which situation you would like to have. Number one, the option would be you start with 1 penny. Every day, the amount you have doubles. So the next day you'll have 2 pennies. The next day you'll have 4 pennies. The next day you'll have 8 pennies. This will go on for 1 month. Or you can just wait to the end of the month and be given $1 million. Which would you pick? Well, before I give you the answer, I'll just point out that this question breaks off of the idea of geometric sequences that hopefully you learned a little bit about yesterday, because the process here is to take a number, take 1, and then you double it, and then you double that. So you're multiplying by 2s or stacking up powers of 2. And that's exactly what happened with those geometric sequences. The ratio R is 2 in this scenario. And you may have noticed, didn't make a deal about it yesterday in the other slides, but you may have noticed that those functions tend to grow pretty quickly. The values that you're getting can get pretty high pretty fast. And so if you looked at this scenario, start with a single penny and double it every day for a month, or just wait to the end of the month and be given $1 million. If you pick the second option, then you do not have belief in the power of geometric sequences, which we are also going to start calling, in a way, exponential functions. Because if you waited out 30 days and you were starting with the penny and doubling the amount you have to 2 cents, 4 cents, 8 cents, etc., etc., by the end of the month you would have, let's see, how do I read this number out? 1,073,741,824 pennies, which is over $10 million. So if you just waited till the end of the month and get $1 million, your friend that picked the first option has 10 million and more. So sorry. Okay, so let's see how we can start putting symbols to this, because that's how we do math, right? We come up with ideas and look for patterns, and then we start saying, well, we're going to look at this more generally. So we have to make names for things and leave spots that we can plug in and, use any number, not just the specific one we started with. But the sequence we just talked about is this 1, 2, 4, 8, 16, 32 business with the pennies. Now, if we look at that as powers of 2, that's just 2 to the first, 2 squared, 2 cubed, because every time you're multiplying by another 2. So this is an example of basically a formula or a recipe where one of the entries in the recipe is getting updated over and over. And so why not just squish that down into a function and call this the function 2 to the x. For x equals 3, we get 2 cubed. For x equals 7, we get 2 to the 7th. Okay? The benefit of changing those exponents to just an unknown, a variable, is that now we can take a look at other values besides nice integers, because 2 raised to the 1.5 is a real number. It's not going to be a nice integer, but it is a number. And so now we can start looking at how all those behave as well. So this sort of thing here, where the variable is now in the exponent, is called an exponential function. Okay, so generally we call it b to the x. B is base, right? This is a case where the letter actually makes sense, unlike m for slope. B for base, okay? That's in the ones we just looked at. B, the base, was 2, okay? Here are some other examples with various bases, like 4 to the x is an exponential function. 1/3 to the x is an exponential function. Now, the difference between these two is that as x gets bigger and bigger and bigger, you can probably imagine that 4 to the x is going to get bigger, bigger, bigger. As x gets bigger and bigger, the 1/3 to the x, though, is going to get smaller and smaller, because you're going to be looking at things like 1/9 and 1/27 and 1/81 and a bunch of numbers in between. Here's one where the base is just a weirdo number, but that's okay. I don't know we'd ever need to use that, but, it's all there. And Remember something about negative exponents. Negative exponents mean to take what is there and flip it upside down, so to speak. So this is stuff you've seen before. 5 to the negative 2 is the same thing as 1 over 5 squared, which is 1/25. And so these x values in the exponents can also be negative numbers as well. So these functions spread out all over the xy plane. Okay, and just for notation's sake, remember that there is a difference between x squared, that's just a power function. That is a monomial, mono for 1. It's got one term in it. 2 to the x is an exponential function. So power functions, exponential functions, totally different things. It all depends on where the variable is. Okay, trends that we're going to look for. If you have an exponential function b to the x, like 2 to the x, if the base b is already bigger than 1, then when you start stacking it up with higher and higher powers in the exponent, the result is going to get larger and larger and larger. Okay. Now, if you start looking at negative exponents, like that example of 5 to the negative 2, and then we say that was 1 over 25, right? Then say we shift to 5 to the negative 3. Well, 5 to the negative 3 is 1 over 5 cubed, which is 1 over 125. So when we are looking at negative values up here in the exponent, as the numbers get larger and larger, but while negative, like negative 4, negative 12, negative 100, the values of b to the x will be getting smaller and smaller as long as b is bigger than 1. If b is a fraction less than 1 in itself, then that's going to reverse, right? You take something that's less than 1 and start raising it to higher and higher powers, you're shrinking the size of the output. But you're going to be doing the inverse when the exponent is negative, and so those results will be getting bigger and bigger. You'll see some examples of this, but there are trends that you want to start recognizing with these. Okay, so just a little bit of practice with evaluating these things. I'm preparing my little tablet thing here. Okay, where's my tablet? There it is. Okay, so I should have had this written down ahead of time. Lesson learned. We're going to evaluate this exponential function, f of x equals b to the x. We're going to ask, when b is 2, what is f of 3? Okay, so the b is 2 part says we are just constructing 2 to the x. That's our function, b to the x. And then when we ask for f of 3, right, we take the function, which we now know is 2 to the x, and plug in x equals 3. So f of 3 is 2 cubed, and where did it go? It's on my tablet, but not on my screen. Okay, there it is. My internet must have just blinked out for a second, so I lost the connection between the tablet and the computer. But if we're looking at the function 2 to the x and we ask for f of 3, that will be 2 cubed. The follow-up question to that was, I believe, having a base of 1/2. So we've got a base of 1/2, and we're going to ask for f of 3. Now, so again, the base of 1/2 means we're looking at f of x is a exponential function, so a base raised to a power that can vary. And so with b is 1/2, this will be 1/2 to the x. That's our function right now. So f of 3 is going to be 1/2 to the 3rd, and that will be 1/8. 1 over 2 cubed, 1 over 2 times 2 times 2, 1 over 8. All right, let's kind of flip those ideas around. And now let's take b equals 2 and ask for f of 1/3. Well, the function is going to be b to the x, so 2 to the x. F of 1/3 says, replace x with 1/3. Okay, 2 to the 3rd. What the heck is that? Well, it's a perfectly good number. We can just leave it as 2 to the 1/3 if we like to. But if you remember about roots, this is also known as the cube root of 2. So we could rewrite it like that, but that's not necessary, right? This is the direct output from the function. It is a perfectly good number. To understand what its value is, say on the number line, you'd probably, I mean, nobody knows what the cube root of 2 is memorized unless you've seen it enough. It's not a nice number. It's a repeating or a never-ending decimal. You just pop it into a calculator or something and get that value back. Okay, and then the last variation of this would be to find f of 1/3 when the base is 1/2. So I'm going to reconstruct our function where the base is 1/2. Now it's down here at the bottom, and then we can see that f of 3 would be 1/2 cubed, and that will be 1/8. 1 over 1 cubed, which is 1 over 2 cubed. Okay, so just doing values of these functions is like any other function. It's a recipe. It's got a bucket that's waiting for you to dump in some input, and then you crank out what the result is. A lot of the results, you'll recognize what they are pretty quickly just from experience. Others, you might need to grab the calculator. You know, whatever works, works. Okay, so I forgot I put 2 extras on the end here. F of 1.5 when b is 4. These are going to be things of that category which are not going to turn out to be something we'll recognize right away. So if our base is 4 and the function is b to the x, so f of 1.5 would be 4 to the 1.5. What that value is right here, I don't know. It's bigger than 4 or less than 16. Because it's in between 4 to the first and 4 squared. It's not going to be a nice number. Well, actually, that's a lie. I think this one turns out to be 8. Okay, but you can't rely. That's just coincidence, right? Because 1/5 is 3/2, and 4 raised to the 3/2 is the square root of 4 cubed, which is 2 cubed. Okay, so that would be 8. So I lied, but it took a lot of work to get there. Normally, you know, something like this, just leave it, or again, punch it into the calculator. The other weirdo case was asking for f of the square root of 2, where the base is 4. So the function would be 4 to the x. We put in square root of 2 for x, and that would be 4 raised to the square root of 2. That is definitely a weird number. But it's a number. It's on the number line somewhere. We could kind of narrow it down. It's going to be in between 4 and 16, right? Just like the one above it. But where exactly? I don't know. Ask a calculator. And so the last thing we want to do is to look at pictures of these graphs. And the pictures tell a really good story because they show you how steep, how fast these functions are to grow in value. Okay, so I'm going to draw a very loose and quick graph of 4 to the x. And again, I'm going to pick some points. I'm not going to make a table. I'm just going to think my way through this, and hopefully you can follow. Okay, so here's the x-axis, here is the y-axis where we're going to graph this function. And I'm just going to pick nice values of x and think them through. Okay, when x is 1, what is the y-coordinate going to be? It's going to be 4 to the first, which is 4, right there. When x is 2, the y value is going to be 4 squared, 4 to the 2. Well, now that's all the way up at 16 already. So if this was just 4, 16 is already way the heck up there. I mean, look how fast this thing is growing. Let's go the other way. When x is 0, we're going to look for the value 4 to the 0. Do you remember what that's going to be? 4 to the 0 will be 1. That is a sort of a definition to bring some sanity to exponential calculations. Any number raised to the 0 is 1. 2 to the 0 is 1. 8 to the 0 is 1. Negative 12 to the 0 is 1. Pi to the 0 is 1. Okay, so don't forget that. Let's go to negative 1. Okay, what value will we have for the function there? Well, that would be 4 raised to the negative 1. As we remember, that's 1/4. So the resulting dot there is going to be pretty tiny. When we go to -2, well, 4 to the -2 is now going to be 1 over 4 squared, which is 1 over 16. That's even smaller, so that's getting really close to the axis. Now I'm going to play connect the dots because I think I've got the trend. Okay, so this is what the graph of 4 to the x looks like. Any other base to the x, 2 to the x, 7 to the x, is going to have this exact same shape. And it's just a question of steepness, right? 7 to the x will get much steeper, much faster than 4 to the x. When we change the base to a fraction, we will see this sort of flip around. So I'm showing you all the 4 varieties, which sounds like, oh my gosh, we're going to do 4 graphs. But the trick is to recognize that these 2 things are already going to be the graphs of the above 2 things. So let me show you the graph of y equals 4 to the -x. Okay, just thinking through what do these values end up being. So I'm not going to make a table. I'm keeping my table up here. Here come my axes. Let's say when x is 0, 4 to the -0 is 4 to the 0, which is 1. So there's that magic point again. Let's go out to x equals 1. Well, now the value of the function that we want is going to be 4 to the -1, which is 1/4. So that's going to be a tiny value. If we go to x equals 2, now we're looking at 4 to the -2 as our function. That's 1 over 4 squared. That's 1 over 16. Now, do these numbers sound familiar? They should, because these were the numbers that were over here on this side of the graph when we just did 4 to the positive x. Okay. When we carry this to the left, we got an x coordinate of -1. 4 to the -1, because this first minus sign is built into the function. This second minus sign is coming from our x coordinate. So that's 4 to the +1 altogether. That's 4. And then over here at -2, we'll get 4 to the -2, which is 4 squared. That's going to be 16, and that's already off the screen. And so when we play connect the dots, we get this. Okay, so basically the story is that all of these graphs are going to look like this or like this. It's the base affects the steepness and which one of those you pick, but they are all very, very, very similar. These bottom 2 that I had pointed at before, say 1/4 to the x, I can show you that, here, let's take 1/4 to the x. We've already drawn these things, although maybe we don't know it at the moment. 1/4 to the x is the same thing as 4 to the -1 to the x, right? You got to remember exponents and fractions and what they do to each other. We can combine these 2 I'm not even showing you the screen, am I? Here we go. Here was the similar graphs. Okay, now here we are. I'm showing you y equals 1/4 to the x, which is the same thing as 4 to the -1 to the x. And then we can mush those exponents together to give us 4 to the -x. Well, we already drew that. That was this one. Okay. So if we go back to this slide, this is one of those nice situations where, oh my gosh, I have to draw 4 graphs. I graph the first 2, but then I can be clever and recognize that the graphs of the bottom 2 are just going to replicate the graphs of the top 2. So see if you can figure out why the graph of 1/4 to the -x is going to end up being the same as the graph of 4 to the x. Okay, just to see if you were catching on some of the details. Every graph we looked at goes through a certain magic point. Do you remember what that point was? It is this point right here. What are its coordinates and why? Think about that one. I'm not going to tell you the answer. After you get some more practice graphing, you'll know it. Okay, so for the moment, worksheet, Google Classroom, you'll be asked to do some graphs of some exponential functions. And then I'll do another video that it'll complicate these things a little bit, but just as an example of the first complication that you might see in some of those graphing problems, and I don't want you to be alarmed by it. If I have a function like y equals 3 to the x, you should recognize that now as an exponential function. I could, right now there is a ghost 1 as a multiple in this function, but I could possibly, I could put a new number in there like 1/2. All that means is to calculate, when I have x is 3, y is going to be 1/2 times 3 to the third. When x is -2, y is going to be 1/2, shut up tux, times 3 to the -2. So this 1/2 is just multiplying all of the 3 to the x's, right? And you've done this before, like you learned how to plot x squared, and then from that shape you could adjust to say plot 4x squared. So don't get messed up by the fact that there might be constant multiples. That just changes the calculation you need to do. And again, a lot of these calculations you'll be able to do in your head, but some of them you'll need to grab a calculator or some app that can run those numbers for you, and that's fine. Mailman must be here.